Okay, so today we are going to be looking at the 3D shapes of molecules. And like I said before, when you have covalent molecules, remember those have to be nonmetals only, which means that there's not a super lot of variety for the simple VSEPR shapes we're going to do. So we're going to focus on ones that have one central atom, and there are more complicated covalent molecules, including things like glucose and fatty acids and all kinds of things inside our body. But it all boils down to the particular shape around a central atom. So even something like glucose, which is carbon-based, is going to have a similar 3D shape to CH4, which has only one carbon, whereas glucose has 6. So we're just going to focus on starting with what the 3D shape looks like around a central atom. So we're only going to focus on covalent. We're not going to worry about the Lewis structures for ionic compounds. Again, because they're so rigid, plus minus, very boring. Okay? So the central atom, central implying like in the middle, and so we can predict the 3D shape based on electron pairs. So they want to be as far apart from each other as possible, but they have to still maintain an attraction to the central nucleus. So this is actually, you can actually measure the bond angles between the surrounding atoms. And if you continue in chemistry, that would be a concept that you might have to deal with. Okay? So we are going to look at two kinds of bonding electron pairs. Okay? Electron pairs. So we have bonding pairs, which we're going to use the short form BP for, and we have lone electron pairs, which we're going to use the short form LP for. Okay? So the Lewis structure, while that's a grade 11 concept, it is good to sketch this so that you know how many bonds there are, which can be easily predicted using the formula. But if you sketch the Lewis structure first, you can see how many there are. And then the number of lone pairs around the central atom. So if you had, let's stick with no carbon. Let's do something like, say, nitrogen. Nitrogen has 5 valence electrons. And what we're going to see is that means it needs to make 3 bonds. But then how do you get 5? 1, 2, 3 bonds. So that means there's 2 left over. How do those look? There's going to be a pair of electrons that are by themselves. So lone, okay? And that is going to be the difference. So in a Lewis structure, it's easier to see which ones are paired up with another atom and which ones are lone or by themselves. So the difference between them really has to do with how they repel electrons and an electron density or negativeness. So bond pairs are more localized between the atomic nuclei, which means that they spread out less. So localized again means they have very minimal movement. Or their location is more set in stone. They don't have a lot of room to move, which means they spread out less. So they're going to have not as big of an impact on both the 3D shape and whether or not that molecule, the overall molecule, is then polar. Whereas when you have a lone pair of electrons, they spread out more. they have what we call a cloud of electron density. So in yesterday's intramolecular note, the one picture showing water it was red in the picture, a big cloud of electrons, and that's literally what it is. The repulsion is greater. It can form sort of this clouded area where the electron density exists. Okay, and it's really spread out. And then that means that the repulsion can be greater and the electron pull is greater, which is going to influence the polarity. And so we're going to count how many bonds are there, how many lone pairs are there. The total number of electron pairs can just help us check our answer, kind of. And then we need something called the VSEPR chart. So if you printed the note off, it's next. I also put it on D2L as by itself. So if it's too small in the note and you want it bigger, great. You can Google this VSEPR chart and you will find plenty of versions. Just be careful, again, some of them will have the bond angles in them, and that's beyond the scope of what we need. Okay, so I just don't want you to complicate things for yourself. So once you use the VSEPR chart, then we're going to draw the best, we're going to do our best to show that it's 3D. Okay, so let's look at this VSEPR chart. And for the VSEPR chart, so you can see here, there are a couple of things. So it does say the total. And again, that just sort of, when you count for total, it just kind of guides you to what row you need. What you're going to want to look at more is how many lone pairs there are and how many bond pairs. So I've put it in here. Okay. So it is kind of hard to see. So again, those of you maybe that don't like tiny writing, you might want to take a look at D2L and find the bigger version, but it's up to you. Even in a normal semester, you would not need to memorize this. You just have to know how to use it. So what we're going to do is count how many lone pairs, how many bond pairs there are, and then determine the shape. If you notice on this picture, there are a couple of weird sort of things here. We have these dashed lines, and we have this solid sort of triangle. Okay, so this is trying to represent that these dashed lines, we say they're going into the plane, and we talked about what plane meant, like the surface, right? Like a plane, like a vector plane, not an airplane. And then the triangle line is trying to show going out of the plane. And really what that's trying to show is opposite. So going into and going out of would be opposite. The straight lines, they are in the plane or flat. So that doesn't really affect how, or really doesn't influence or affect how polarity occurs in terms of whether the molecule has balance or symmetry or not. Okay, so I think let's do an example. So you're going to do, I recommend sketching the Lewis structure. Then we're going to determine the BP or the lone pair or bonding pairs, LP lone pairs. We'll use the total to help guide us through the chart. But the total, it's just kind of a summary. And then we're going to write the VSEPR name and draw the VSEPR structure the best we can. Okay, so BF3. And first of all, you might be thinking to yourself, B, that is metalloid. Yes, and metalloids can have properties of metals, both metals and nonmetals, right? So BF3 we're going to use boron with 3 valence electrons, and then of course fluorine has 7. Okay, so the central atom is the atom that's written first. We talked about that in the review lesson. And so boron has 3 bonds, and then fluorine has 7. But back up here, it said we're going to count, I'm even going to pick a different color. We're going to count the number of bond pairs around the central atom and the number of lone pairs around the central atom. So in this case, the central atom is boron, which means that's the one that I'm going to care about. So fluorine, even though it has 7 valence electrons, you don't really need to draw all 7. What we need, oops, I shouldn't have drawn it there, sorry. What we need to know is how many it's going to share. So you can still think of it like how many it's going to gain. That doesn't really matter if that's how your brain thinks of this. So fluorine only needs to gain 1, so that's the only one I'm going to draw. Why? Because it's not central, it's not in the middle, it's not going to influence the VSEPR shape. Okay, so how many bonds are there? There are 3. Okay, so I'll use my highlighter because this isn't a board, but then I'm going to erase it. So how many bonds are there? There's 1, 2, 3. Actually, I can leave that. Is there any lone pairs around boron? No. So that is 3 plus 0 is 3. Okay? You have to use the VSEPR chart. So I don't expect you to memorize this, although you might find, to be honest, that you start to see patterns, and especially the ones at the top of the chart, they are really, really common, and there's not a lot of variety. Okay, so maybe you will have them memorized, but that is not an expectation. Okay, so we're going to take 303 and go into our chart. So total number is going to draw our attention to the 3rd row, and then we're going to look for 0 lone pairs and 3 bond pairs, and there it is, trigonal planar. So the E and the X, this is general, so we are not going to do E's and X's. We're going to do B and F because that's what our picture is, or our molecule is. And you can see here that even though they're all flat, straight lines, which means they're flat, it's still drawn kind of like a peace sign, right? So each of these angles in here is as far apart as possible while also maintaining the bond attraction. So when you draw the VSEPR shape, first of all, we're going to write trigonal planar because that's what it's called. And then when you draw the VSEPR structure, even though over in the Lewis, I kind of drew it like almost like a cross but missing the bottom, that's not really 3D how it looks. So you want to do your best and draw it like a peace sign, like it looks in this chart, okay? So that's why the chart is so useful. You just have to know how to use it. So let's do another one. We're going to do CH4. Carbon has 4 valence electrons. Hydrogen has 1. So I'm going to quickly sketch what that looks like. Again, I only care about the bond pairs and lone pairs around the carbon. So how many bond pairs are there? 1, 2, 3, 4. Actually, we'll highlight that. 4 bond pairs. Woo, that is not what I wanted to do, sorry. And there are 0 lone pairs, so the total is 4. 4 plus 0 is 4. And when you go and look back to our chart, I'm going to erase the other one I had. Again, the total can kind of guide you to where you should look. So 4 total, 4 bond pairs, 0 lone pairs means tetrahedral. And again, take a look. So now tetrahedral has 2 hydrogens, or 2 of the bonds in the same plane. One's coming out at you and one's going into. So you want to do your best and draw that shape. So 2 in the same plane, one coming out at you and one going into. Okay? Does it really matter if you put the one coming out on the other side and the one that's flat on the left-hand side of the carbon? No. But most people just try to follow the chart that I've given you. Okay? All right, so far we haven't had any lone pairs. Let's take a look and get into some that have some lone pairs. So here we have NH3. Nitrogen has 5 valence electrons. It's in the 5th column. Hydrogen has 1. So nitrogen with 5. Never eat shredded wheat. And then go back and start pairing them up. So now when you make the bonds with hydrogen, we have these bond pairs here, but now we also have this lone pair up here, and that is going to have a big influence on the VSEPR shape. So there are 3 bond pairs, which starts out the same way as trigonal planar, but now that presence of 1 lone pair, you're going to see what happens to this shape. So 3 plus 1 is 4. So back to our chart. I'm going to erase the other one. So now we're still in the 4th row, but now this time we have 3 bond pairs and 1 lone pair. What kind of shape is that? Trigonal pyramid. And the important part about trigonal pyramid is you can see that this lone pair sort of sits at the top of the molecule and repels all the other atoms away from it. And that's true. The lone pair has that spread out electron cloud of density, and that has a big influence on the 3D shape. This molecule now has a lot of its negativeness, or its electron density, concentrated at the top, and the atoms are constant, and the bond pairs, which are localized, are concentrated at the bottom, which means that now this molecule has very little symmetry. So the sharing in the overall molecule is no longer equal. So that is how we are going to determine whether an overall molecule is polar or not, we'll do that later. So this is the VSEPR name, trigonal pyramid. And then again, use your chart and try to draw it as close to that as possible. So we want one of the lone pairs at the top, one of the hydrogens in the same plane, one coming out at you, and one going into. Okay? Remember, water is a weird structure because oxygen is going to be the central atom. Oops. But it's the only case. That's weird with hydrogen first. And it has 6 electrons. Hydrogen has 1. Give it a quick sketch. Okay, so now this time I'll continue with the same sort of thing. We have a bond here, we have a bond there, and we have this time 2 lone pairs. So the formula, like H2O, NH3, sort of helps us with the number of bonds around the central atom, but then the Lewis structure can help with how many lone pairs there are. So how many bond pairs? 2. And how many lone pairs? 2. So we still have a total of 4. So you can see that, you know, the total lone pairs is not super unique. However, it helps get us what row to go to. So we're still in the 4th row on our VSEPR chart. But this time we've got 2 bond pairs, 2 lone pairs, so now it's angular. And again, very not so symmetrical. At the top here of the molecule are the lone pairs, and then the 2 atoms at the bottom are so repelled from that big electron density of the lone pairs. Okay. So the majority of the molecules in the world are some version of trigonal pyramid, tetrahedron, and angular. So let's say you have a large carbon molecule, for example, with hydrogens on it, then it would just be a bunch of tetrahedrons stuck together. So it's when really you start to break the octet rule, like we did with the advanced Lewis structures, note that things start to be a little less straightforward. So we're going to do these 2 examples are special cases, okay? So selenium is in the same column as oxygen. It has 6 valence electrons. And then chlorine has 7. It only needs 1. So when you do these, you'd be like, oh, Miss Todd, I think it's supposed to be SeCl2, but it's not. So this is one of those weird Lewis structures that breaks the octet rule. So when you have Cl4, that means that chlorine is going to break apart this lone pair and start to bond. So when you do something like this in a sketching kind of way, then you can quickly just start to fill it in with the already paired up electrons. So I'll always give you the formula. So look at how many chlorines are supposed to be. There's supposed to be 4, okay? So what you don't want to do is something like this. So let's say I put a chlorine here, and then I'm going to say, oh, let's put a chlorine up here. And then there are 2 electrons by themselves. It doesn't work like that. You can't do that. Okay, so actually I'm just going to erase this whole one. Okay, so you just want to keep, so you would never have, let's say, SeCl3. That's not a thing because you would never leave a lone electron by itself. Lone electrons are bad. They're free radicals, and they can wreak all kinds of havoc. So how many bonds are there? Again, predicted by the formula, there are 4. And then because of those extra chlorines, now there's only 1 lone pair for a total of 5. So these shapes are very weird. So what you might find is if you do a lot of the homework, maybe you might actually have tetrahedral, trigonal planar, trigonal pyramid, angular. You might actually have those memorized, whereas this one, especially with the 5s, once you start to get down here, these weird shapes, you probably will not have those memorized, and that makes sense, okay? Because they're much more rare. So I already forget what, 4 and 1. So we have 4 bond pairs and 1 lone pair. What's that going to be? Seesaw. Okay? So again, do your very best to draw it as it is on the chart there. So selenium in the middle. Here's the lone pair repelling everything as far away from it as can be. Okay? So the ones that break the octet rule are a little bit strange. That's why too, I didn't say this when I started to sketch the Lewis structures, but that's why you might find it helpful to do the bubble way, because you can just kind of keep going and filling them in. Same thing with carbon dioxide. Now, carbon dioxide is one that we would have done in grade 11, but it does have double bonds, so it is not an easy one necessarily. Carbon has 4 valence electrons, oxygen has 6. So carbon in the middle. Again, this is maybe a situation where bubbles are a little bit more straightforward. Let's pair these ones up. But then in order for oxygen to be full, then we need to pair it up there. And then there's 2 more bonds. Okay, so that's really kind of strange. When you do the counting of the pairs, when you have a double bond, so in order to make the VSEPR chart work every single time, you'll notice at the bottom, there's this little thing right here. Okay, double and triple bonds count as 1 bond pair each. Okay, so in order to make our chart work with what really actually happens, then what we're going to do is count these 2 as 1 bond pair and these 2 as 1 bond pair. Oh, sorry. 2 bond pairs, 0 lone pairs. So the shape that we actually get is 2 and 0 lone pairs, which is linear. And in a real way, the carbon dioxide molecule is linear, or it has 180 degrees between its atoms. Like this bond is 180 degrees, right? So that's how we can always use this chart to rectify the situation. But when you draw it, you want to make sure it makes sense. So even though it's linear, but in the picture it only has 1 bond, you can draw the double bonds so that it makes sense. Okay, but draw it linear or straight, 180 degrees. That's another very rare, very weird one. Okay. So the other part to this is deciding whether a molecule is going to be polar. So when we did the delta E and G, that was to determine if a bond was polar. Now we're looking at, is a molecule polar? Okay, so polar again is unequal sharing, nonpolar is equal sharing. And if you have the same atoms or atoms with very similar electronegativity, they're going to pull electrons equally. And so we often have to use the VSEPR shape, and whether or not there is lone pairs or not, or symmetry or not, to see if it's going to be polar or not. So if one atom pulls electrons out, so we said that was a triangle, and the same atom pulls electrons in, which is the dotted lines, the overall pulling is canceled out, or we say that the molecule is then symmetrical. which means it's like a teeter-totter. It balances. One pulls out, one pulls in. You're going to get symmetry, and the molecule is balanced. So let's say you have, well, we just did carbon tetrachloride, or CH4. Let's do that one, because we already drew this. Okay. Oops. So we have into, we have pull out of, and so that is symmetrical. You might say, well, what about the other ones? Yes, if all the atoms are in the same plane, so that means flat or straight lines, like these two up here, they are the same plane. The molecule is said to be nonpolar. Okay, so if you are asked to say what it is, polar or non, it's nonpolar. And if you're asked to give a brief reason, you can literally say molecule is symmetrical. Okay? Or the in and out cancel out. The overall pulling is canceled out. Whatever you would like. Very brief reasons. Okay? So another example here is trigonal planar. So we did BF3. And sometimes people think because 3 is an odd number, okay, well then odd isn't symmetrical, right? However, this is where they're all in the same plane. So you would say nonpolar, all F atoms are in the same plane. You could say all F atoms are flat. That means the same thing. That is terrible handwriting here. Sorry. I'm just going to fix that. Okay. So, pretty obvious. No lone pairs. It's either all straight lines or there's straight lines and coming out and going into. How do you know if something is polar? Well, generally speaking, we never want to say always. In chemistry, we never give those kinds of absolutes. Lone pairs, they have very large electron pull, and that's generally going to make the molecule polar. You can also actually talk about that the molecule is no longer symmetrical anymore. So we did NH3. Okay, so you can even, if you want, you can even draw in this cloud of electrons here at the top, but you don't need to. You would say polar. Oh, oops. Let me draw it like your chart shows. Polar, you can say lots of things. Lone pair have great electron pull. You could say molecule is unsymmetrical. I would accept that because the top of the molecule contains the pull of the lone pairs and the bottom does not. What else could you say? That's probably it. You might also see something called, it's called a dipole moment. And really what it's just trying to show or trying to emphasize that the pull of electrons is in a certain direction. So it kind of looks like an arrow. So the electron pull is towards the top of the molecule. And the way that they show, it shows the difference is they put a plus sign at the bottom. So it's like the electron pull or the negative charge, negative pull, is towards the top of the molecule. That is certainly also a valid reason. However, that is not my expectation. But if you are a person who likes to watch Crash Course, Khan Academy, whatever, they might talk about dipole moments and the direction of electron pull in terms and show it using this kind of weird arrow. That's fine too, or you can just be as brief as I was in the bottom. Okay? So sketching the Lewis structure will help you figure out the number of bond pairs and lone pairs, and making sure you know how to use that VSEPR chart, which even in a normal semester, you would not need to memorize. Not for the test, not for the exam, nothing. Okay? So just know how to use it. So work on the worksheet and the textbook questions and let me know if you have any questions. Okay? Thank you.